So I'll try to get started here. Where would you guys like to start? How about mission 5? Let's look at mission 5. So mostly mission 5 is about what? It's about, well, sorry, I must make this Adobe Acrobat submit to my will. There we go. All right, so the first bunch of problems were what? They're just find critical numbers, find intervals of increase and decrease, right? And classify local max, min, or neither, right? I don't know if there was a neither in this batch of examples that I gave you guys, actually. But let's look through that. So, like problem 93, we have f of x. We differentiate it, right? We factor it.
I have one question.
Sure.
Concave up, the interval for that is the same thing as increasing, right?
No, concave up and increasing are totally different things.
They are.
Yeah. You can have concave up and increasing. You can have concave up and decreasing.
I didn't know that.
Yeah, they're different. Concave up is going to be when the second derivative is positive, but increasing we see from first derivatives being positive. So the second and the first derivative, they don't have to match.
Oh, okay.
Just like a function and its derivative don't have to match. Let's see here. So for this one, I found critical numbers 0 and 4/3, you know. I drew the sign chart then. I marked the places where the derivative is 0, and then I checked each subregion to see whether it's positive or negative. So this shows me increasing between 0 and 4/3 and decreasing elsewhere. And then because you're changing from minuses to pluses, right? That's a minimum. Pluses to minuses, as we read from left to right, that's going to be going up and then going down. That's the maximum. So that's the first derivative test, right? If you have a critical number where you stay plus to one side and plus to the other, or minus to one side and minus to the other, then it's neither. But I don't remember that. I don't remember coming across that as I was solving this homework, actually. Sorry about that. Well, I stopped asking you guys to classify local max or min in the last part of this homework. I just slipped my mind. I really should have, because it would have been sort of, I did anyway to make my graphs, all right? But, so for this one, I got 0 plus or minus 2, which then gave me this sign chart, and, this is where it's increasing, that's where it's decreasing. Yeah, any questions about these? I'm going to kind of just go on because I think the later problems probably require more discussion. This one's a little bit more interesting in the sense that for this one, we actually have a critical number which is outside the domain of the function and indeed outside the domain of the derivative. Remember, critical numbers can happen either places where the derivative is 0 or places where the derivative is not defined. Those are both possible places for the sign of the derivative to change signs. So that's why we have to include 2 in this story, although, ironically, the derivative did not change signs at 2, right? But we shouldn't say that it's increasing from 1 to 3, because that would be saying that 2 is in the domain of the function, and which is not true. Yeah. So that's a minor oversight. Like, I wouldn't take a lot of, I won't take any points off in your homework for that. But I'd probably take off like 5-10% on the test, everything else being right. Now, what next here? So again, so f of 1 and f of 3 are local maximums. And I really should have said in my solution here that 2, f of 2 is neither, right? It's not defined. I guess I kind of did here, but I'm just fussing. It's fine. Problem 96, this one's, got some what's the word? Like it depends on how you interpret it. If I make this problem easier, I can make it easier by just telling you, well, this is just for 0 to 2 pi. You know, like limiting the scope. But I didn't limit the scope, so in principle, you should have tried to figure out for all x that this is defined, you know, where the critical number is. Well, there's a critical number anytime you have tangent equal to 1 over root 3. So pi over 6 does that, because sine of a half, sine of pi over 6 is a half, and cosine of pi over 6 is root 3 over 2, so the halves cancel, you get 1 over root 3. And of course, you could just take your calculator, do inverse tangent of 1 over root 3, you get pi over 6, right? But then the thing is that the tangent function has period pi. So if you have one solution for tangent, you can always add any integer multiple of pi to it, all right? Because the tangent function repeats itself every pi. You know this? No? Well, I'll tell you now. So tangent looks like it's got vertical asymptotes at pi over 2, at minus pi over 2, right? And it goes through 0 here. But it also goes through 0 here and here. And it also has a vertical asymptote over here at 3 pi over 2, and so forth. Minus 3 pi over 2. It goes through 0 here at minus pi. This is at pi. And so like the graph of tangent, something like this. And it just keeps doing that. These are supposed to be all the same width, you know, I just can't maintain. So the thing is, if you pick any point, well, like 1 over root 3 is, it's right here-ish. So like as you go through here, all these points of intersection are solutions. This fundamental one is pi over 6, but this is like pi plus pi over 6. This over here is minus pi plus pi over 6. So generally speaking, the general solution, pi over 6 plus n times pi. So tangent of that is 1 over root 3. The tangent has period pi. That means, like more generally, this is an identity for tangent. The tangent of theta plus any integer multiple of pi is just equal to tangent theta again. So pi is the period of the tangent function. It's how often it repeats. So that's why I have infinitely many solutions. As you can see, sometimes the tangent's positive. Let's see here. Now the tangent being equal to 1 over root 3 is equivalent to the equation df dx equal to 0, right? But the sign chart has to come from df dx. So the df dx is this minus root 3 sine x plus cosine x, right? So I check points in each subinterval to come up with these signs, and I find out f is increasing on those and it's decreasing on those. And like if I wanted to write it more systematically in terms of an integer parameterization, there it is, right? So, any event. Now I haven't pushed writing solution sets for trig equations in terms of an integer parameter in here, so I don't see myself testing on that. But it's something you should be aware of, and it's something that will become more important as you take calculus 2. All right, moving on. 97, I differentiate. And I made a stupid arithmetic mistake when I first did this, why there's some weird whiting out. I made the problem more complicated by like keeping a 4 here. That just messed it up. But once you factor it properly, it's not bad. 0 and 6. So there's supposed to be a 6 here. See sometimes I white stuff out, and then I neglect to like write back in what I want. But there's obviously supposed to be a 6 here, right? And where else? Here. Can you find any of the other 6s? Maybe that's it. So here, this one actually has the concavity question, right? So here, increasing on minus infinity to 0, and also 0 to 6, all right? And decreasing on, I got to that's still a holdover. That's supposed to be 6. After class, I'll go edit this yet again and repost it with the corrections, okay? Like I said, I had a mistake. I had left the 4 in front of the x, and that made me think it was 3/2 for the critical number, which is not true. And anyway, I got like all the way to the end of the problem before I noticed this, but it only impacts actually parts A and B, and then the graph. So part C, to figure out possible points of inflection, you set the second derivative equal to 0. So second derivative is 48x minus 12x squared. So when I'm differentiating polynomial, I'll always go for like the standard form for differentiating. Almost without exception, that's easier. But when I do that, I can pull out a 12x. I got 12 minus 4x, so x equals 0 and x equals to 4, the places where that could be 0, which is to say that's the places where the second derivative could change signs. Changing signs for the second derivative is changing concavity. So it's concave down over here, it's concave up in here, it's concave down over here, which means that that's going to give a point of inflection, and that's going to give a point of inflection. And of course, I can read off the intervals of concavity there as well. So the inflection points are at x equals 0 and x equals to 4. To actually find the points, which you kind of want to for the sake of graphing, you have to plug the numbers into the function, right? Not the second derivative, not the first derivative, but the function, because that's the thing we're going to graph, right? Y equals f of x, not y equals f prime of x, not y equals f prime prime of x, right? We graph the function in part E. So well, f of 0 is 0. Woohoo! That was easy. But when you plug in 4 into the formula, I got this, which gives me 256. So the origin and 4, 256 are the inflection points. Yeah, at this point, and I was writing my solution, I was like, I forgot to ask them to classify min-max for these problems. But it would have been helpful because they're going to make a graph, right? Minimums and maximums are helpful for graphing. So that would have been helpful. I said, well, f of 6 is 432. If you go back up to the sign chart, there's only one max, right? Here. So 0 is not a min or a max, it's neither, right? It turns out to be an inflection point. That doesn't have to happen. Not everything that's a neither a max or a min is an inflection point. They may or may not be. There is really no direct automatic link between things you can say about the second derivative and things you can say about the first derivative. I mean, there are things that can be said, but don't assume that they have to match. Like, it's just not the case, okay? I mean, they are linked because the second derivative describes the change in the first derivative. But that's a more subtle relation than you might realize. In any event, here it is. And it really shouldn't be so pokey on the top, you know? But so like 0, 0 is a point of inflection. See, it's changing from concave down to concave up there. And this is also a point of inflection. So it's changing from concave up here to concave down over here again, right? That's the maximum at 6 of 432. It's easy to see there's an x-intercept at 8, 0 from like the original formula, right? And, you know, there you go. This one is cubic, so I found critical numbers 4 and minus 3, made the sign chart, differentiated it again to find possible points of inflection from the second derivative. And so, 1/2 is the place where the f prime prime can be 0, just that, right? And so if you plug in like 0, you get a negative from that formula, right? So it's negative over here. And if you plug in, I don't know, 1, 2 minus 1 is positive. It's positive to the right of the point. So it's concave up from 1/2 to infinity. It's concave down from -1/2 to 1/2, minus infinity to 1/2 rather. And at x equals to 1/2, we have an inflection point. To find the inflection point, we have to plug 1/2 into the formula for f, which is no longer pictured here. And it works out to -73. Yeah. Now, on the test, if I say, where's the inflection point, and you tell me it's at 1/2, I'm going to give you significant credit for that. But if I say graph carefully, including inflection points, and you don't label the y-coordinate on it, you're probably going to lose a little bit of something. All right, but so I'm trying to give you some at least partly careful graphs here, as careful as I could come up with in my state of somewhat, I don't know, I'm not thinking super clearly at the moment. I'll just say that, okay, guys? So f of -3 is 270. It's a local max. F of 4 works out to -416. It's a local min. By the first derivative test applied to the sign chart, f of 0 is 0, just that you can see from the original formula. There's no constant term. And so the graph looks something like this. You notice I didn't force myself to have the same scale on the y and x. That's helpful. You don't have to have the same scale on the x and the y axis, right? You don't want to either, because if you made the same scale, you could never really see what's going on, because everything interesting goes on here from like 1 to, like basically what, -10 to 10 in the x, but the features in the y are on the order of hundreds, right? So you definitely don't want to use the same scale for both axes if you want to see the shape. Yeah. And notice that I've labeled the inflection point, right? Labeled the inflection point. I've labeled the minimum, the maximum. It would be better if I had said here, parentheses like minimum, maximum. You know, more labeling is good if I ask you to carefully graph something. Now, if I just ask you for a sketch, then I'm much more kind of easygoing about it. So this one, we got to use the product rule. We get a critical number of 1/2. The second derivative, the second derivative, see, I slip up sometimes and call the places where the second derivative is 0 critical numbers, but they're not. Technically speaking, they are possible points of inflection. So anyway, there is an inflection point at 1. Oh, look, L'Hopital's rule. Woohoo! It was helpful here. See, because to figure out what happens to this function long term, I need to take the limit as x goes to infinity, right? And this one, it works out to 0, because the exponential wins. In a battle of exponentials versus polynomials, always bet on the exponentials, because they'll win eventually. Excuse me. So there you go. The local max is 0.5. Is at 0.5. Its value is 0.18 approximately. There's a point of inflection at x equals to 1. And it happens at 1 when y is about 0.135. And this is a very sad attempt of a sketch of this. I could attempt another one here today if you'd like. It'll probably also be sad, though. I don't know. So it's supposed to look so like 1/2, 1, and it's what, 0.5 at the max, and it's got a point of inflection at what, 0.13? It's like here-ish. So it's supposed to do something like, I always have trouble like with the asymptote, but see, it shouldn't. My asymptotes inadvertently curl back up. That's not actually happening. Like they should always be kind of like getting closer and closer and closer, you know, to the x-axis, but they never get there, right? So my graph has some kind of, so it's not really there, right? This one was a little bit challenging, and so we got to think through it a little bit. df dx, product rule, chain rule, right? Derivative of cosine is minus sine, but then chain rule says I multiply by 2x minus 4. So if that derivative is going to be 0, it's either going to be 0 because the sine is 0, right? And I call the inside thing theta. Either because sine of theta is 0, where theta is that quadratic, or because 2x minus 4 is equal to 0, which happens when x equals to 2. I labeled the domain of interest J just because I didn't want to keep writing it. All right? So if you look at it, when can sine be 0? Well, sine can be 0 at integer multiples of pi. So I'm going to start looking at integer multiples of pi, see what happens. I look at theta equal to 0, which is just this. That gives me factoring x minus 1, x minus 3, which gives me x equals 1 and 3 possible critical numbers. Are they in J? Are they relevant? They are, right? Those are in J. Notice I put J in decimals up there so we can quickly decide whether or not things we're finding are actually in the relevant domain. Okay, so that's theta equals 0. Theta equals to pi. Well, that gives me pi is equal to x squared minus 4x plus 3. Well, I'm going to use the quadratic formula to solve that. And the quadratic formula gives me 2 plus or minus 1/2 root 4 plus 4 pi. Of course, the 4 factors out to give you 2 there. So you get about 4.03 or minus 0.03. Again, those are in J. We got more. We got a couple more critical numbers. And then finally, I get to 2 pi, and that actually gives me the endpoints of J, which are not included. So at this point, I know I'm done. I found all the critical numbers, because if I keep going further out, if I go to like theta equals to, minus pi or to 3 pi, I'm going to get x's which are further out. All right. You can try it if you want, but that's what's going to happen. So we find 5 critical numbers in J, and also there's critical numbers at the edge of J. That's relevant to us as we're thinking about how to graph. There's like a 0 right outside J. There's a 0 right outside J. All right. And so you can see where f is increasing and decreasing. I would also point out, though, that whenever sine of theta was 0, this is something important to know from trigonometry. If your sine is 0, cosine must be plus or minus 1. If cosine is 0, sine is plus or minus 1. This is forced upon you from the fact that sine squared plus cosine squared is 1. It is inevitable. So many of the critical numbers, right? In fact, all the critical numbers except for 2 came from sine being 0. Right? Now, the original function was cosine theta. Right? So if sine theta is 0, that means cosine theta is plus or minus 1 at any of the critical numbers where we had sine theta equal to 0. And so those were like the minus 0.031, the 1, the 3, the 4.06 or whatever it was 1, right? And also the endpoint ones, which were not quite included, right? The ones at the edge of J. Those were also critical numbers that had the form sine of 2 pi equal to 0. But the one in the middle, 2, is not such a thing. So that one, I actually have to plug in to f to get 0.54. I originally used degree mode, and it was like, huh? It's almost 1. And I was like, wait a minute. I'm in degree mode. So I put it into radian mode, and then I got that, which was better. So you get this kind of toothy-looking graph. But anyway. Now, of course, you guys have graphing calculators, yes? No? Okay, good. That is a good thing. All right, so I've been so programmed to expect the answer yes from my trigonometry class, So this one here, what are we supposed to do? We're supposed to use the closed interval test. These problems are much easier. It's not a graphing question. It's just a closed interval test question. How do you do these? Make sure your function's continuous. Find the critical numbers, right? So you differentiate it and try to figure out where the derivative is 0. This one has critical numbers 0, 3, and 6. You notice I accidentally changed the interval here to 0 to 5, but in your problem set it's 0 to 4. So like I just transcribed it wrong, but it doesn't change the solution, so I didn't edit it. So if it is, so I solved a slightly different problem than the one it was assigned. That's what I'm trying to say. But 0 and 3 are inside here, so they're relevant. 6 is not. So we ignore 6, all right? And then you check the value of the function at the endpoints and also any critical number in between, which is in this case 3. And you get 0, you get 81, I get 25. Which is the biggest, which is the smallest? Well, 0 is the smallest, 81 is the biggest, right? I believe. And so by the closed interval test, f of 0 is the minimum and f of 3 is the maximum of the function f of x on the closed interval 0 to 5. Next one, same song and dance. We differentiate, we set the derivative equal to 0 to find critical numbers. Here you have to make a common denominator. You get x minus 1 over x squared plus 1. X squared plus 1 cannot be 0, right? So the denominator is harmless. It's always non-zero, right? But x equal to 1 gives us a critical number up top. That gives us 0 in the numerator. So x equals 1 is a critical number. It's also in the interval 0 to 5, so it's relevant. So we check f of 0, f of 1, f of 5. And we decide which one's biggest, which one's smallest. Decimals are helpful. So the one is like minus 0.439, the other one's like 0.255 approximately, and the other is 0. So which is the smallest? Well, the smallest is the negative one, of course. And so when I say smallest and largest, I'm talking about if you put all the numbers on the number line, which is the furthest to the left, which one's the furthest to the right. I'm not talking about magnitude, I'm talking about like ordering on the real line. Anyway, so there you go. There's your min, there's your max. That's the closed set test. All right. Problem 3, verify the mean value theorem for f of x. So what you're trying to do here is you're trying to find a c such that f prime of c is equal to f of 3 minus f of 1 over 3 minus 1, right? This is the claim of the mean value theorem, that there exists a point where the slope of the function is equal to the average slope of the function over 1 to 3, right? This is the slope of the secant line from 1 to 3. And so what that amounts to here is I need to solve the equation 3c squared plus 6c plus 1, that's f prime of c, equal to f of 3 minus f of 1 over 3 minus 1, which happens to be 26. So I've got a quadratic equation to solve. We can solve it. It may or may not be pretty, but we can solve it. In fact, it's not that pretty, but the answers are about 4.055 and minus 2.055. Now, I could give you answers in terms of exact radicals and stuff, but I don't think it adds much to the discussion here, so I stuck with a decimal presentation. This is the relevant one because it's inside 1 to 3. That I don't care about. It's extraneous to the discussion. The larger point is you can check that the box solution is in fact the one we want, because when you plug it into the derivative, guess what happens? You get back 25.999, which to the limits of the accuracy of the numerical methods we're using here is 26. So that's what's meant when someone asks you to verify a theorem. It's to actually work through the problem and show that the claim of the theorem is met in the function that you have there. So, problem 104, I removed. Let us not speak of it because it's just bad. It's bad. It's bad. It's bad. Bad. Very bad. Okay, so guys, what would you like me to do? There's two different paths we can go down. I can either go back to mission 3 and talk about earlier stuff, which is just, I think, mission 4, right? Yeah, we should probably talk about mission 4. I'm never able to cover everything in the review day. Like, it's just not possible, but I'll try to get what I can. So in here, I noticed some of you skipped problems 84 and 85. That is unwise. That is almost always something like that on the test. Let's look at those, yeah? Oh, I should mention 82. Here's x's position. How do you find velocity and acceleration? One derivative finds you velocity. And then differentiate again, right? So dv dt is acceleration. That gives you acceleration. In other words, acceleration is the second derivative of the position. The velocity is the first derivative. That's it. Implicit differentiation, you just differentiate with respect to x. Anytime you have y in your differentiation, that picks up a dy dx term, right? You have to then pay attention to all those, solve for the dy dx, and that's the answer. It's just that. It's the same thing pretty much every time with the implicit differentiation problems. So, and the formula is typically some kind of mess in terms of x and y. Excuse me. Here's the problem I want to talk about. So actually, I don't want to talk about that one to start with. Let's talk about this one to start with. It's easier. So show that the derivative of inverse hyperbolic tangent is 1 over 1 minus x squared. So what we do is, let me check my silly camera, see if I need to zoom out or not. It never shows up very good. There's just this projector and my camera does not like each other. They'll never be friends. So we set y equal to the object of, we set y equal to whatever you're trying to differentiate, right? In this case, inverse hyperbolic tangent. Then I take the hyperbolic tangent of both sides. So that gives me tangent of y equals to x. Next step, I differentiate with respect to x implicitly. The derivative of hyperbolic tangent is hyperbolic secant squared. All right? And then because I'm differentiating with respect to x, I pick up a dy dx. On the right-hand side, I've got 1 because dx is 1, right? I usually write that out, but I haven't here, whatever. And then I solve for dy dx because that's what I'm trying to find, right? I'm trying to find the derivative of inverse hyperbolic tangent. Well, that's 1 over secant squared, but hyperbolic secant squared. But hyperbolic secant squared is, in fact, equal to 1 minus hyperbolic tangent squared. Hey, what happened? Come on, really? Well, this step right here is what? What do you think about this right here? Is this true? See what I'm circling? That is backwards, isn't it? I was supposed to put 1 minus hyperbolic secant squared there, right? And did I redeem myself in the next step? I did, right? So I must have been editing it and not noticed that I needed to white out that as well. So as you can see, there's some whiteout going on here. Whenever you see whiteout in one part of the problem, be suspicious that I missed something. All right, but anyway, the point is 1 minus x squared is what tangent is x, right? Hyperbolic tangent is x. So that's 1 over 1 minus x squared, but that's what we're trying to show. So, yay. This one is similar, but the added wrinkle is that when you do the algebra, trying to get back from y to x, you face a plus or minus issue. Right? So if you let y equals inverse sine, the sine of y is x. So differentiate both sides with respect to x. Ooh, look, so many more details in the solution. Cosine y dy dx equal to 1, which tells me that dy dx is 1 over cosine y. Sorry. And then, so solving for cosine gives me plus or minus the square root of 1 minus sine squared, right? Which is plus or minus 1 over square root of 1 minus x squared. But the thing is, we know sine is increasing where the inverse sine is defined as its inverse, from minus pi over 2 to pi over 2. So that means that the inverse sign must also increase because of what we discussed in class. Remember, when you differentiate the rule that relates this function and its inverse function, you get the product of the derivative of the function composed of the inverse function, and the inverse function must be equal to 1. So either they're both plus or they're both minus. So the function and the inverse function must be either both matching, increasing and increasing, or decreasing and decreasing. You can't have the situation where you have a function which is increasing and its inverse function is decreasing. Nonsense. You can't do it. So anyway, because the sign is increasing on its, where we, where the inverse sign serves as its inverse, it forces us to choose the plus, and so there you go. There's also problems like this, right, where you have no choice but to use implicit differentiation because we don't have rules of differentiation for x to the function of x, right? There's no differentiation rule for that except do implicit differentiation. So you set y equal to the thing, you take the natural log of both sides because that's how to deal with this kind of thing. Natural logs turn, powers into products, right? So with that move, all of a sudden we've got log y is x cos x, log x. We differentiate and then solve for dy dx, and then you have it. So anytime you've got x to a function of x, what you want to do is say y equals to that, take the natural log of it, and use implicit differentiation. That's how to solve these kind of problems. You should be sure you know what logarithmic differentiation is. What is it? It's when we take the logarithm of the expression, use properties of logs to break products into sums and divisions into differences and pull down powers, etc. Right? Use properties of the logarithm to algebraically simplify the log of the thing we're trying to differentiate. Then we differentiate the logarithm and then finally solve for dy dx. Right? This is logarithmic differentiation. And like here's an example of it, of course. If I was to just differentiate that directly, I'd need triple product rule, and it's kind of a mess. If I take the log of it, I've got a sum of these three things. One of them simplifies really nicely, because log of e to the 3x is just 3 to the x. Then I got log sine x. I pull the third down, 1/3 log of that. And then the other important thing to remember for the logarithmic differentiation is the chain rule for the logarithm, right? Which is this. If we have natural log of u, the chain rule for the logarithm is just this. We take the derivative of the inside function, right? And we divide by the inside function. So like that's how we differentiate the logarithms. I always that's how I write the chain rule as a matter of, least writing. And then, of course, after everything's said and done, you got the 1 over y dy dx on the left-hand side. You want to multiply the y to the other side, so you have your answer. There it is. And problem 88 is just the same, right? It's just the same. Problem 89, I forgot to put numbers in, so I made it symbolic. But usually with this kind of thing, people will tell you like the volume rate of change and the radius rate of change, and then say, what's the rate of change of the height or something, Like typically in these problems, we give you numerical things for everything but one thing and ask you to find the other thing. That's often what's done. But anyway, the larger point is if you have a algebraic relation which relates various variables in a model, right? And then those variables could in principle have a time dependence, right? Well, then you can differentiate such an equation with respect to time and relate the rates. So if there's an algebraic relation between like model variables, that implies a differential relation between them as well through differentiation. That's it. And this is what related rates is. It's just that. Like this one, if you've got a cube and its surface area is 6x squared, right? So if I want to see how the surface area is changing, I differentiate the surface area, I called it A, and I get 12x dx dt. But I'm told that dx dt is 3, and I'm told that x is equal to 4 at the time I'm interested, and so there you go, 144 centimeters squared per second. We also talked about these ladder down sliding on the wall problems, right? Again, the key is the algebraic relation. Since it's a right vertical wall, x squared plus y squared is the length of the ladder squared, and that relates the rate at which the base is moving to the rate which the top is sliding. And then we worked some of these car problems, which again is based on the distance between the car by the Pythagorean theorem is x squared plus y squared equals s squared. Difference being, unlike the ladders, the length of the ladder is not changing, right? I mean, you could make a changeable ladder length problem if you wanted to be malevolent. You could make your students work the sliding ladder where the ladder is not sliding down a vertical wall, but like a tilted wall. I've done that. I didn't do it to you guys, but I've done that. It's in the notes. But anyway, you know, again, you find the relation between the variables and then identify velocities or as rates of change, dx dt, dy dt, and then put it all together. So let's see here. So mission 3 is hopefully starting to be your happy place at this point. I don't think it was when it happened, but I hope if you go back and look at mission 3, it's far less mysterious now, right?
So this is going to be over everything we've learned?
Pretty much, yeah. I mean, I don't see myself testing on the definition of the derivative, but it definitely will test on like linearity, the product rule, the power rule, different derivatives, sine, cosine, tangent, secant, cosecant, cotangent, all the functions. 2 to the x, log base 2 of x, you know, hyperbolic cosine, hyperbolic sine, all the full assembly of characters that we've gone over. So I think if you go back and look at mission 3, you guys are going to be probably okay with it at this point. Or at least I hope you're okay with it. Is there anything in here you want to talk about? I mean, it's mostly product rule, quotient rule, eventually, you know, some constants riding along. Here I didn't say A and B were constants, I said they were functions. That's why we had dA dx and dB dx here. If I said A and B were constants, then those terms would be gone. And you just have 2xa and b e to the x, b times ex. Chain rule, different kind of chain rule, but chain rule. Whoa. More complicated problem, but chain rules. See, sometimes the first thing is to break it into pieces which are more manageable, you know?
The second term there also chain rule.
This is, first thing I'm doing is the sum rule, like the derivative of the sum is the sum of the derivatives, which I sometimes call linearity. Then after that, the product rule on the first term, right? I got to do product rule because I've got x times cosine x cubed. And over here, I have to do the chain rule because my outside function is this minus the 1/2 power, but the inside function is e to the minus 3x plus 2. So that's why I do minus 1/2 and then minus 1/2 minus 1, which is minus 3/2.
How did you get that?
Power rule.
1/2 over.
This one?
No, that 1 over.
Oh, changing that to that?
Yeah.
Oh, that's just because 1 over the square root is the minus 1/2 power. So if I have 1 over the square root of x, yeah, that's 1 over x to the 1/2, which is also x to the minus 1/2. And the same is true when you replace x with a bunch of stuff. It's okay, we're all learning. So that's how I did that. But let's see here. But yeah, there's many, I mean, problem 75 is such a rude awakening after doing for these last 3 problems. It's like little hill, I just keep climbing, where's the top? You know? But anyway, there it is. And then there's this one. So like whenever you're differentiating, you got to be aware, like, what's the outside function? What's going on? Because if there's an outside function where other things are inside, you have to deal with the outside function first in the chain rule, right? So here the outside function is everything's being cubed, so I must address that first. So it's 3 times whatever all that stuff is squared times the derivative of the inside function, which happens to be cosine of sine of 3x here. So, and then I do the chain rule on that. Well, now the outside function's cosine. So I do, and the inside function sine of 3x, so I do minus sine of 3x, and I have to differentiate the inside function. And then, well, that gives me the cosine 3x. But the inside function there's still another inside function, yet another one, which is 3x, right? So that brings out the 3. So 3 times 3 is 9 at the end. So if you can work this kind of nested chain rule problem, to me it means you really understand Calculus 1. Like, this is the mark of an A student, somebody who can just do this. It takes practice, and like a lot of it is just understanding like the pattern of what you're looking at, that you're looking at a function being composed with another one, you know. And it just takes practice. So anyway, I hope as you go back and look at mission 3, you see that, I mean, some of these problems are just complicated, but all of the steps, they're either linearity, product rule, quotient rule, or chain rule. And it's just repeating that, right? And algebra things, like you said. And that is true. Algebraic identifications. That's a big thing, you know, recognizing that that square root can be converted to -1/2 because we have power rule for x to the n. You know, so unless you know a differentiation rule for 1/square root of x, you get stuck on that, right? You got to be able to convert it to a power. And then problem 80 is, you know, listen, guys, I don't, well, anyway, it is what it is. If there's a question on Carathéodory, it would be a bonus question. I think we have enough else going on. I probably won't test on that in all likelihood this semester. So that brings us to what? Microsoft Edge. Ew, I feel dirty. Let's see here. Let's look at mission 6. We got, what, 20 minutes? Is that right? 18 minutes? How many minutes we got? 23 minutes? Oh, wow, that computer's really off. Okay, so the way I see it, I can either spend 15 minutes solving the first 2 problems, or I could solve 18 minutes solving problems 107 to 116. What would you like me to do? I suggest I solve problems 107 to 116, and I write up the solution for the first 2 so you can look at it later. I wish I already had it to look at with you, but I am just not catching up yet. This stupid sickness is wearing me down. So, I mean, I wanted to have mission 6 solution done before class today, obviously, right? But it did not come together. So let's work the L'Hopital problems. I think that's probably the best use of our time. All right, so 107. We've got the limit as t goes to 0 of what? Sine, oh man, t squared over t. So what happens if you apply L'Hopital's? Can we apply L'Hopital's rule? What type is it? Very good. So applying L'Hopital's rule, what we got? We've got 2t cosine of t squared by the chain rule, right? And 1 downstairs. At this point, we're done, because you can plug in 0. What's cosine of 0? It's just 1, right? So you got 2 times 0 times 1, also known as 0. So that's 107. 108. I will write down and then ask if you had any questions about the previous one. Oh, man. Fine. Stay. Come on, stay. All right, so we got, what are we looking at here? Limit as x goes to 1. What am I doing? I have a printout of this thing. Let me put this thing to bed. There we go. I feel better. Whoa. Hey, hey. Tell no one. All right, so x minus 1 log x minus sine pi x. Ooh. I brought the pi out. So what type are we looking at? When you hit log, natural log of 1 is 0. Sine of pi, also 0. So we got 0 in the denominator. We got 0 in the numerator. Type 0 over 0. Well, this is made to order, L'Hopital. So we'll differentiate the top. What we got? 1. Differentiate the bottom. What you got? You got 1 over x minus pi cosine pi x. Yeah. Now, can I plug 1 into that? I think I can. That gives me 1 over 1 minus pi, well, plus pi. See, because cosine of pi is minus 1, so the minus gives me a plus, right? Problem 109, I think, is a very... I'm glad this happened for us today, because every so often I have a sense of regret as I don't manage to talk about the derivative of 2 to the something or 3 to the something right before the test, because some students have the wrong idea that just because I don't talk about something right before the test, that means it's not on the test. That doesn't really mean that. It just means I haven't talked about it. I can't talk about everything all the time. Okay, anyway, so this, what are we looking at here? We got 0 on the top. We plug in 0, right? And we get 2 to the 0. 2 to the 0 is what? 2 to the 0 equals 1. So type 0 over 0, right? So we apply L'Hopital's rule, type 0 over 0, and that gives us the limit as x goes to 1. I have to do the product rule, right? So I get 2 to the x plus x times the derivative of 2 to the x. What's the derivative of 2 to the x? Do you remember? Let me fix my silly camera. Focus more on where I am at the moment. What is going on here? Right, so we do x times what? Natural log of 2 times 2 to the x, yeah? And how about the denominator? We've got natural log of 2, right? Times 2 to the x. Now the question is, are we done? Can we plug in 1 into that? Is it defined? I think so, actually. So we plug in 1, and we get 2 plus 2 log 2 divided by 2 log 2, which is just a number. Problem 110, we've got limit as x goes to 0 from the right of natural log of x squared plus 2x divided by log x. So as x goes to 0, we're looking at log of 0 and log of 0. What happens with log of 0? This is what log looks like, right? Whoa. Log looks like this. So, log x goes to minus infinity as x goes to 0 from the right, yeah? So what we're looking at here is something we can apply L'Hopital's rule to, type infinity over infinity. So differentiate those. How does it go? Limit as x goes to 0 from the right. Huge fraction. All right. I've got 2x plus 2 divided by x squared plus 2x. I'm using that chain rule for the log that I told you about a second ago, and 1 over x. Now that's a compound fraction. How do we simplify it into a single nice organized fraction? We just go, okay, so that's x times 2x plus 2 divided by, well, x squared plus 2x times 1. So that's the limit as x goes to 0 from the right of, well, oh, look at that. X times 2x plus 2 divided by x times x plus 2, right? I can factor an x out in the denominator. Now, if you didn't see to do that, you could also apply L'Hopital's rule again. But anyway, I'm going to use some algebra there, cancel it. And with that, I can plug in 0. 0 plus 2 over 0 plus 2. So the answer here is 1. Ooh, problem 111 looks fun. Let's try that one out. So we're supposed to calculate the limit, x goes to 0 from the right, of log 2x minus the natural log of x plus 1. How'd you guys solve this one? Well, here's how I'll solve it. This is x goes to 0 from the right of the natural log of the quotient, 2x, divided by x plus 1 by properties of the logs, right? But then the natural log is continuous, so I can pass the limit inside the log. Right? And we've been doing a lot of L'Hopital's rules. Let me do a little bit of algebra here more. You could settle this limit inside with L'Hopital's, but I'm just going to go ahead and do an algebra step. And what I'm going to do